All right, so welcome and thanks for coming to my session. We're going to talk about containers today. If you have questions or anything while we're going through the slides, feel free to raise your hand or shout out. I can kind of see people in the back. If I miss you, just kind of make some noise. All right, so my name is Dan, and I work for a company called 7 Signal, and we make Wi-Fi optimization software, which is a lot of fun, and we use containers to package and deploy our software. I also work on a couple open source projects, build packs, and then Paketo build packs, which are related to containers, and that's kind of where I started and learned quite a bit about them. Before I get into the actual slides, I would just wanted to give a link to the slides if anybody is looking for them. The demos are in here as well. So I'll just pause for a second. All right. I'll put them in the channel on Discord too, if you didn't get a chance to grab them. All right, so we're here today to talk about containers. I think that may have been obvious from the title, but just to reiterate, before I get into anything more, what is people's general experience with containers? Who's using them in some way, shape, or form? Okay. Who's kind of doing just the bare minimum? Like, I need to use this, but I may not really know how it works. It just kind of does what it does. Okay. And who's like a container expert? Who's been using them for 10 years and has all sorts of experience? Okay, cool. No one to call me out. That's great. I think what, the general experience that people have here is pretty common from what I've seen. A lot of people, they know about containers. They may see them at work. They probably use them at work, but it's kind of a means to an end. They use them to get a job done. Once the job's done, they move on to the next thing, like writing code, delivering features, things like that. And so I thought it'd be great in this talk to kind of dig into containers a bit and kind of get a chance to cover all those underpinnings and the cool stuff that makes all that stuff work for us. So again, you can get by with just kind of the bare minimum, for your containers. You can, run a Docker build file or a Docker file that you copied from somewhere on the internet, and build your container and run it, and life will be just fine. That's kind of a nice thing about them. But there's some great things to understanding the technology a little bit more in depth as well. You can evaluate different container technologies a lot faster when you understand kind of the mechanics of how it all works. So if your company is looking at, hosting your software on, a cloud provider or something like that, you can kind of evaluate the different offerings they have and figure out, what makes sense to you. You can also design your systems and your code to work better. There is such thing as a bad image. You can make them in ways that don't work great, that have inefficiencies in them and things like that. So understanding how that works too can allow you to kind of build better stuff and really streamline what you're doing. And sometimes, which is important for your employer, you can actually save cost doing that too. The other thing is that they are pretty much everywhere. Containers are all over the place, and so you're probably going to run into them at some point. And so just understanding that technology, can really go a long way, both in making it easier to implement what you're trying to do, but also just, help with your career as well. So what's a container? I think that's a good place to start. My wife saw my slides and she asked me exactly that. And it is kind of like a Tupperware container. It's just something that you are using. It's an abstraction to kind of package up what you're doing. And at the core of it, you have essentially an isolated process on your system. So it's just like any other process on your system, but there are restrictions and things that are put on top of it. I also find it's easy to explain what a container is by what it's not, and containers are not Docker. It's a very common kind of terminology slip that you'll hear. Docker's a company, Docker's a piece of software, which is great, and it lets you run containers, but it's not the container itself. And same with a Docker file. Sometimes you'll hear people use the term Docker file, and it's not really a container. That's what you use to build containers. So again, that maybe me being a little picky, but it does help to have a good grasp of the terminology. So when you're in the room, giving a presentation to your colleagues, you sound like you know all the details. The other thing that a container is not, it's not a VM. It's very common for people to conceptualize a container as a VM, and that's kind of a great starting point because they both do some similar things. They both give you some nice isolation and protection from other things that are running on your system, but they kind of fundamentally work at different levels. A VM is isolating things at a very low level. It's running an entirely separate operating system, so there's kind of a whole bunch of extra overhead with that as well. Containers are at the process level, like I said, they isolate an individual process, and so they can share some things, like they can share the same host operating system and the same kernel. And so you get some efficiencies there where a VM might take you a minute to start, a container can start up in fractions of a second. So again, just to reiterate, what is a container? First thing you should think is an isolated process. It's running on your system. If you're on the host system, you can use PS and look at it. And so it's just another process. But the system is putting some nice restrictions in place for you to make it so that it's, from the perspective of that process, it doesn't see everything else that's going on your system. All right, just a quick overview of some of the strengths and weaknesses. Like I mentioned, containers are pretty fast, pretty quick to run. They're everywhere, and they're also standardized, which is really great. The Open Container Initiative has a number of standards around containers so that they're very interoperable. Isolation is not as good as VMs or some other technologies, but oftentimes it's enough. Other challenges you can run into are kind of around noisy neighbor. It's kind of easy for one process to get real busy and maybe impact other things on that host, even though there is some isolation there. Classic use cases where containers are a great fit. If you're testing something and you just want to run it and not screw up your laptop, you can run it in a container. It's great because, when you're done, you just delete that container and everything goes away. It's great if you need like a different distro. Maybe you're hosting things on Debian and your third-party software requires Red Hat, so you can get a Red Hat container, you can run that container on a Debian host, and that software won't know any wiser. If you want to isolate, or sandbox some code, that's a great thing. Maybe you don't fully trust it, you can run it in a container. That's awesome too. You can also use it to run Linux software on your Mac or Windows machine. We'll talk a little bit more about that in a bit, but it's nice for kind of cross-platform, distribution of things. A few things where, maybe if you're seeing this, maybe it's not the best use case for containers. Desktop apps are really hard to package in a container, because they need to have a screen and a window and show you stuff. And that's tricky to get access to all that in a container. CLI apps, same way. It's just kind of awkward to run a CLI app that probably wants to look at your file system when it can't see your file system. And then other things like stuff that has very strict hardware requirements. So if you have like real-time guarantees that your software needs, containers are probably going to add more overhead, and you're not going to be able to accommodate that. And so maybe direct hardware is a better approach for that software. GPUs are another one where you can kind of do it, but you're going to have some fun getting that all configured and working right. So if you have stuff like an LLM that's running in a GPU, if you don't have some special sauce going above and beyond that with your container, it'll be tricky to run it. So we have our isolated process. What do we need to get one of those running? First thing you need are some files. Most likely, most things don't run without any files. And for that, we have what's called a container image. And the container image is probably something that if you're distributing your software in containers that you've produced, maybe in your CI pipelines, with Docker build or something like that. And it's just kind of a collection of your application files, the things it depends on, and then some configuration on top of that. So you might tell it some environment variables or a command it needs to run, things like that. And those just get paired together in the container image. The really cool thing about container images, and one of the things that you can really take advantage of when you are kind of building your systems, is that they are created using layers. And so it's kind of like the layers of a cake, or like the layers in this photo. They layer up on top of each other, and so you can have files in each layer, but they're kind of distributed and treated separately. And so you can kind of stack things on top of each other and do some really cool stuff. Like if your bottom layer has your, maybe your Ubuntu system, you can layer your application code on top of that, maybe some config on top of that. And if you need to update your Ubuntu layer, you can just swap out that bottom layer. You don't have to actually go and rebuild your application if you don't want to. So there's some really cool things that you can do there. And this is kind of what I talked about previously. So you can share these layers. If you have maybe a base image, your particular version of Linux that you like to use, you can put that on the bottom, and then you can stack your applications on top of that. And these are, I don't know, this isn't the best graphic, but essentially these are different images. You've got one for each application, but they all share that same base layer. And what's really cool about that is your base layer is packaged and distributed separately. And so if something changes in your application layer, that base layer doesn't necessarily have to change. And so you can do some things that are really efficient. And some of the systems that you'll deploy to that the cloud providers have can be really efficient about not having to re-download those layers, or not even having to reload those layers when they reload your application. So like AWS Lambda is a good example. Amazon provides a base image that they suggest people use if you're going to package your Lambdas as containers. And the really great thing about using that is then when your Lambda loads, it doesn't have to load that base layer because it already has it. Amazon guarantees that the hosts that are running those will already have that layer. And so all they have to do is slide your application files into the environment and run those. And it can save time, and time on Lambda is money. So it can really allow you to do some nice cost savings there. One kind of word of warning about stacking these layers is that you don't want to go too crazy, because things in those layers can overlap. And so if you have a base image that has a nice up-to-date version of OpenSSL, and you pull in another layer on top of that that has a, I don't know, dodgy, unupdated version of OpenSSL, that higher layer will mask what's in the lower layer. And so those dodgy, bad OpenSSL files will mask your updated ones. And so you have to take some caution with the way that you're installing, the way that you're composing these layers, so that you don't run into issues like that, because it can be a problem. And some of the image scanning tools that are out there will help you with this. They'll look through all of the layers and not just kind of the aggregate of them. So that can be helpful too. No, each layer is just a set of files. So the base image doesn't even have to be an operating system. If my application is a static binary that doesn't need any other files, the base layer could literally be just that binary. It can be any set of files that makes sense for your application. It is very common to use one of the published operating system, Linux distribution layers as your base, because it gives you a lot of great things like like a certificate chain, so that you have, proper, trusting when you're making, HTTP calls and things like that. So that's very common. The other really cool thing is that every layer in your image is hashed. And so each layer is hashed individually, which allows these tools to understand what's in those layers at a really quick glance. Because if anything in one of those layers changes, down to the byte, that hash is going to change and it's going to be different. And so it allows them to do lots of optimizations, like sharing that base layer, like I mentioned earlier, and just making sure that it is what it says it is. Containers provide this kind of security guarantee as well, that someone hasn't come in and shoved some extra files in, with your application that shouldn't be there. In addition to those individual layer hashes, there's a hash for the entire container as well. And so not just the individual layers, but the aggregation of those layers is hashed. And so you can't even swap those layers out with changing that hash, and in turn alerting someone that something has changed here. So in addition to layers, a really cool thing that you can do with containers is called volume mounts. And so volume mounts are basically a way where you can take some additional stuff and pass it into that container and say, make this available at XYZ path. It's really great for like passing in configuration. A very common thing you'll see if you're looking at images on Docker Hub, like with Nginx, for example, is that they'll say, volume mount your Nginx config file into this location. And if you do that, when the container starts, it will just magically pick up the configuration you mapped in. And so they let you do some really cool stuff like that. And there's almost no restrictions on what you can volume map and where you can map it. Again, you do have some concerns with things like overwriting stuff. If you volume map something in and it overwrites files you need, you could break your application, or you could introduce security vulnerabilities if you're mapping in something that isn't secure. So you do have to be careful, and you also have to check what your provider or what your container orchestrator supports, because they don't all support volume mounts, and some of them do it in different ways. Like Amazon ECS does it in a way that's really kind of a pain and makes it not as useful. All right, so the first demo we're going to take a look at here is just going to be deconstructing a container image. And I wanted to show this because I feel like container images kind of have this mystique that they're like, they just black box, they do what they're supposed to do, and that's it. But they're really not that complicated. Container images are really just, oh, you guys can't see that, can you? Yeah, 1 second, I'm going to have to switch to mirroring. How about now? Okay, great. Let me make that bigger. All right, so container, let me see, where was I at? So container images are really nothing special. They're just archives. And so what we can do is just pull one apart ourselves. So if we make a directory here, we can go and fetch a container image. I'm just doing this for speed. This Scopio command is cool. It gives you all sorts of different commands for interacting with container registries. Right here, we're just telling it, copy one of those container images down and turn it into a tar file for us, which is the OCI standard format. So we do that, and then we have our tar file right here, and we can just extract that with plain old tar. And if we look at what we see is the contents of that tar file. And this is the standard OCI layout. This file here is kind of the marker trait of that. So you'll see that in all of the images. It doesn't really do anything beyond that. And then you get an index file, and that index file can give you all sorts of cool stuff. It's kind of like if you look at your Docker inspect on an image, it will give you that similar sort of information. So in this case, actually what we get is a what's called an image manifest. This is telling us the blob file for our images. So I guess maybe another thing to explain about these is that once you get in here, you have this index file and you have this blobs directory, and everything is just a blob. So there's text files that are blobs, there's actual layers that are blobs, and you can find all of that based on these hashes. So if we were to take one of these hashes, and look at it, we can see there's a file there. We can look at the file, it's JSON data, and we can look at that. And this is more information about that image. So in this case, we can see where our config is and where our layers are. And this is just kind of what I mentioned before. You have files and you have config, and that's really what the image is. And if we wanted to dig in more and look at our layer data, we can do that. Again, it's there. And in this case, it's just another tar file. We can extract those files. I'll just show you them. But those are all the files, and this is a base Ubuntu image, so you'll see all the familiar stuff you'd see on the root file system of an Ubuntu image. And that is really about it for them. It's really kind of simple. And when you see, when you run Docker pull or something like that, you see it going through these phases where it's fetching and extracting. All it's doing is going through and pulling these files out and putting them into a file system. And it has its kind of own way of storing them so that it can do things efficiently, but that's what it's doing under the covers. If we wanted to, we could modify this image. We could recalculate the hashes. We could zip the files back up, and we would have a new image. I wouldn't recommend it because it's tedious to get all that stuff just right, but that is what the tools are doing for you when you do a Docker build. They are managing all those hashes and just zipping things up in the way that they need to be. Any questions about pulling apart a container? Ooh, I gotta switch back. All right. So we've got our images. We know of images. Now we want to get some images. And the way to do that is through what's called a container registry. And container registries are another thing that I feel like kind of have this mystic persona that they do all this cool stuff. But really, a container registry is just a REST-y HTTP service. When you have something like Docker and it's going and it's pulling these images, all it's doing is making a few HTTP calls on your behalf and grabbing some files. And so the really cool thing about that is we've seen kind of a plethora of different container registries that are available. I'm running one right now locally on my machine because we don't have internet access, but you have Docker Hub, GitHub has container registry, and there's tons of other ones that are free that you can host images on. All the cloud providers have them as well for their systems. So you have all these different options for container registries, but they all work the same. And that is, again, because of those OCI specifications. There's one called the distribution spec, which kind of shows how these services are supposed to work and guarantees that the endpoints are the same. And what I want to show in the next demo is how those APIs work. They are pretty straightforward, and I think it's just kind of cool to see. Again, you kind of see what's going on behind the scenes when your Docker pull is running. And all right. right, so I put some scripts together because, not because it's all that complicated or anything, but just because I wanted to kind of streamline this demo a little bit. And before I show you the scripts, there's actually two sets of them here if you're looking at these later. The ones that start with DH are for Docker Hub, and the other ones are the OCI specs. All of, I shouldn't say all, probably all of the container registries that you'll find out there implement their own kind of APIs on top of the specification, because the specification doesn't necessarily include everything. So your APIs for like fetching users or managing your organization, those usually happen at your are specific to that provider you're using. But those providers also give you some APIs for similar things too, like listing tags and stuff like that. So there's some overlap. The ones that you probably want, though, are the OCI ones. Those are the ones that allow you to do things like actually fetch an image. And so those are the ones that I particularly find more useful. If you're talking to a container registry like Docker Hub or something, you will have to fetch a token. So there is a script in here for fetching an API key. I'm not using that here because, like I said, I'm just using a local registry. So if you use a local registry, you can skip that step too. But basically, we can run one of these scripts. We can tell it what image we want to see. We're telling it we want the Ubuntu image, and then it'll come back with the tags for that image. Not super fancy, but again, it's really simple to do this stuff. It's one curl request, and we're just saying give us the tags for that particular image. So there's no great magic in doing Docker images or something like that. Now, if we want to do something more fun, we can grab a manifest for one of these. So we can go and get the manifest. Now, the manifest here is very similar to the one that we looked at when we took the image apart. The thing that we'll notice that's different here is that because we're looking at the registry can actually serve up multiple kind of different variations of an image, and those usually center around the platform and OS architecture. So in this case, we can see there's our Linux AMD 64, there's unknown, I don't know what that is, there's Linux ARM, etc. So we can then go and pick which one of those we want. So if we want to pick a particular one of those, and we can go and fetch that. And this is exactly what we looked at before. This is the same manifest that we pulled out of the image. It's just being served up by the container registry. And so we can see the same things. We can see the layers. We can see the config. And then we can go and fetch those things as well. And the really cool thing about this is that for Docker to know what's in your image, it doesn't have to fetch the entire image. It can just fetch this manifest, and it can use that to know what's in the image. It knows what layers are part of that. So let's say your image gets, a new version of your image gets published. Docker can go out, can fetch this manifest, and it can look and see which layers have changed. And so it then only needs to pull those layers that have changed, which is really nice. I don't know if anyone remembers downloading VM images back in the day, but you'd download like a gigabyte of files, and then a week later they'd update it, and you'd have to download the whole gigabyte again. It wasn't a great experience. And if we want to pull one of these things to actually get some data, let me grab this one here. We can do that too. And in this script, I just have it running tar for me because I'm lazy, but we can see the same stuff gets output here. It's writing all that stuff out. And if you want to see what's going on there, because I promise there's no magic, all we're doing again is one command. We're fetching a blob, again, which is consistent with the way that that file structure is inside of the image as well. And then we are just making a directory, and we're extracting that blob into that directory. And that's how we go and fetch a layer. So again, when you do a Docker pull, you're seeing it downloading and extracting images. This is what it's doing. It's just making these API calls for you. All right. So, kind of the last thing, running containers. It's a little bit important because eventually you want to actually do something with these containers. And before I get into exactly how we do that, I do want to just clarify a term that I may have used previously that I like. I don't know if I'm the only one that says it, but container orchestrator. And I like this term because it's kind of a generic way of saying something that runs a container for you. And there are so many of these now out there that I kind of feel like there has to be a term for it. You know, sometimes people will say Docker when they mean running the container somewhere, and it can just get a little confusing. But there are so many of these places where you can run a container image. You know, besides your local machine with Docker or Podman, you can use Kubernetes, you can use the cloud providers. There's like PaaS technologies that will take an image and just run it for you, all sorts of stuff. So I kind of collectively refer to those all as container orchestrators. And when you pick a container orchestrator, it's going to give you some things in order to run those containers, the first of which is the Linux kernel. And that is kind of a hard requirement to run containers. And you might be thinking, well, wait a minute, I can run containers on my Mac or on Windows. And you're right, you can. But the trick is that those systems are running them in a VM for you. So you have Docker Desktop or something like that running, and it's actually running a VM in the background for you. That is a Linux VM where those are actually running. And most of the time, this is seamless, and it doesn't really matter until you go to volume mount something and you realize that you're not actually running it on that system. Some of the tools actually have ways to make volume mounts a little bit easier, but that's kind of the one rough edge of that. Anyway, the reason you need the Linux kernel is because it gives us these primitives for running an isolated process and for running that container. We get cgroups, namespaces, capabilities, seccomp, and AppArmor, which are all the different things that it is using to isolate that process for us. Cgroups are for resource control, so that's kind of how you would say, like, you only get this much CPU time and this much memory. Namespaces are a way to kind of make that process not be able to see other things on your computer. So you know, typically when you run something with Docker, you don't see anything else that's running on that host. That's kind of the de facto way that most of these container orchestrators will run your software. But the really cool thing about namespaces that I like is that you don't have to do that. Namespaces you can pick and choose. So you can pick and choose and say, like, I want to run this process, and you know, I don't want it to see other processes on my system, but maybe it can share the same network. And then you can do really cool things like, you know, have sidecar processes that run and stuff like that. And actually, if anyone's worked with Kubernetes, that's the way that pods operate. Pods have a shared network space, which is courtesy of these namespace features. The other thing is that I've kind of referred to it as this isolated process, but you can run multiple processes in a typical Docker, you know, quote unquote container. And namespaces are kind of how that magic works, because you can allow those two processes and just those two processes to see each other. When you are using them, it appears like they're running in the same kind of logical container. But they are really both just isolated processes that just happen to be able to see what each other's doing. The other things on here are a little more under the covers. Capabilities and seccomp are a way that a lot of the container runtimes will basically take permissions away from your container, restrict what they can do. You know, you don't want the container, you don't want people to be able to break out of the containers, so they will take a lot of permissions away that might be sketchy, that might give people the ability to do that sort of thing. And AppArmor is kind of one step farther than that. That allows you to even isolate things down to like the process or specific network level. All right, so after we have our Linux kernel and stuff, you know, we need to present some sort of file system to this container. It's pretty rare when something doesn't need any files at all. So we're going to make some sort of file system. That's where our container image comes in. We get the files from that container image. These tools will take those images, kind of, you know, or organize those layers in a way that makes sense to the tool, and then present them to the image. And there's this neat system call in Linux is called pivot root, which basically does the hard work here. And so you call this pivot root syscall, and the process that's running that used to be able to see the host file system now sees whatever you give it. So it's pivoting out that entire root file system, which I think is really kind of neat. And then, like I mentioned before, you might package some configuration with your image, but you probably want some additional configuration on top of that. Maybe you're going to volume mount some configuration in. Maybe you're going to set some environment variables, just at runtime, that sort of thing. You can usually pass more configuration to these tools. If it's Docker, it's on the command line. Maybe there's a YAML file you use, or maybe some other config that your container orchestrator gives to you. And that's really about it. That's what these tools need to run your container, to run your isolated process for you. The easy button is, if you're locally, is just Docker run, or Podman run if you're using Podman. But you can deploy things to Kubernetes the same way, or any of your cloud providers, that you might happen to be using at work. And these tools will handle all of those details that we talked about. But I don't have time to get into it, which would be fun if I did, but I don't. There is a hard way. You can do these things yourself, and there are tutorials you can find online that'll walk you through basically how to write software that makes your own container. I think it's really cool that you can actually kind of build those things yourself. If you are, looking at building kind of a system for running applications in your company or something like that, you might find it useful to take a little more control over some of these things, to be able to kind of adjust how you want the namespaces configured, or, how you want the cgroups configured, and all that stuff. And it's all there. You can do it. Besides using the APIs, there's also tools that you can use that kind of help there. There's a cool one called Unshare that lets you adjust namespaces. There's a libcgroup that provides some CLI tools as well, so you can mess with cgroups. And Docker and Podman also give some control over that stuff. So there are some flags you can set to Docker run, that would change like the memory settings and the CPU settings and stuff like that. All right, so I've got one last demo and one last slide, which is just questions. So I'm just going to open it for questions real quick, if there are any. Otherwise, I'll show the last demo. Okay. All right, so the last demo here, we're just going to take a look at cgroups, and we're going to take a look at namespaces. And an easy way to set them, like I mentioned, is with Docker run. They do expose these to you. And so there's a flag for CPUs, and there's a flag for memory. Oh, am I not? Oh, thank you. It didn't switch over. Perfect. Thank you. All right, so this is the command I was just explaining. We've got Podman run, Docker run is the same. It has these flags here for setting the CPU count and the memory count. And they will do kind of what you expect. CPU is a little bit tricky. I don't know that I have time to dig into that too much, but we'll see if I can circle back to that. And so the container I just started is running just a little web server, and what it's doing is it's going in and it's pulling the cgroup information out of the container. So it's kind of giving us, from the perspective of that process, what it sees, what it's allowed to use. And that's one of the cool things about cgroups, is that they expose all that information. The kernel just dumps it out in files in the proc file system, so you can go in and read those and look at them and see what's going on, which is really neat. In this case, we can see we've got our max CPU set here, and we've got our memory set down here. And so that's a gigabyte in bytes, I believe. And then if we like refresh this a bunch of times, you can see things like system time and user usage and all that stuff changing. Let me go ahead and restart this with different limits to prove I'm not lying. And if we restart or refresh, we can see limits have changed. You know, we've got our 4 CPU limit now, and we've got our increased memory. And the really cool thing about the fact that this information is exposed is that language runtimes and applications can read that stuff to take advantage of it and automatically adjust their tuning and scaling so that all you have to do is increase those limits on your container and things will just magically increase or decrease accordingly to run your application, you know, which is a really great feature. You know, when you're in the midst of an outage or something, you know, the last thing you want to have to remember to do is go in and tweak a bunch of configuration settings. So to have, to be able to just increase, you know, your, the size of your image with your cloud provider and restart and have everything just magically adjust is really nice. All right, so the last thing is namespaces. And for this one, I'm just going to start a shell. And if you'll notice, what I did was pass this privilege flag in. You would not normally want to do this because privileged, as you might expect, gives you a lot of extra privileges, and you don't normally want a container to have those. But in this demo, I'm going to make another container inside my container because you can just keep nesting containers as much as you want, and that does require extra privileges to do that. So if I run hostname in this container, we can see that I'm in the outer container. And now if I run the unshare tool that I was talking about and start a new shell, I'm in a new shell, and if I run hostname, we'll see, hey, it still says outer container. I don't like that, so I'm going to change it. All right, so now let's run hostname again. And there we go. All right, cool. I've got my container that I like. That's great. I can also look at my processes here and see what I'm running. So in this case, we can see my current processes here, and then we can see the parent process here. And that's because this container unshare-u is not doing a full isolation like you'd get with Docker run. It's only setting one of the namespaces for I think it's UTS, and that is allowing us to see these other processes, which, you know, in some cases might be nice. You might want to see that stuff. But the cool thing is that if I exit out of this and I run hostname again, I didn't actually change the hostname in my outer container. It's still set, still the same thing. I didn't have to go back and reset that. It's just that this -u flag, the UTS setting, it host namespace will allow you to have a unique hostname. And so we've isolated that hostname part of our container. We've isolated the hostname to what our inner process sees to be that specific thing. And so that allows us to kind of change it and update it, but not disturb what's going on outside of it. And so you can do all sorts of different things. Unshare, I don't know if I have man pages here, but unshare lets you set all sorts of different settings with your different namespaces. And so you can just kind of fiddle around with that if you are building your own kind of you know, container runtime or something like that. This is a nice way to kind of just play around with stuff and see how the different settings work. And that's basically it. I mean, there's obviously a lot more to it, but in 45 minutes, that's kind of what I can cover. Any other questions?
Quick clarification question.
Yeah.
So, earlier you said the actual, for example, AWS Lambda implementation is you have already a container running, and then the Lambda files are just extra layers on top, and then that one is run at
I'm not totally sure I follow, but basically, Lambda will take one way of running a Lambda is with a container. So you can give it a container, and then it knows how, because it's a standard format, to extract those layers and files and then copy them into the environment where it runs them. I don't want to pretend like I understand what's going on behind the covers there, but it's able to then do that in a more efficient way. So if you use their shared base layer, it doesn't have to always copy that stuff. It doesn't have to always go fetch that stuff, extract it, and then copy it into your image. It usually just has it handy because it's such a common layer that's used on Lambda. Sure.
Do you have any suggestions on limiting disk space when you're running lots of containers at once? That's the one thing we've noticed switching.
So he asked about limiting disk space when running lots of containers. I would say that's probably more of a question for your whatever the orchestration tool is that you're using. You know, they might have something there. I do know that like some of the tools I've used in the past have struggled with that as well, because it's really easy for users to like, hey, I just made a 10 gig image and I don't even realize. And then now it goes and downloads all that and fills up your server space. Yeah, I'm not sure that I have a good answer for that, but yeah. Cool. All right, well, thanks everyone.